Hi everyone, thanks for coming, welcome to Red Track and welcome to my talk on empowering junior testers, strategies for uncovering critical vulnerabilities in web applications. So, before I begin, I'm going to keep looking over here first of all because of where my notes are, so I apologise if that looks strange with the camera away on that. A little bit of motivation first for why I even am here today, why I wanted to talk about this particular topic. Throughout my career, as my journey to becoming a penetration tester, I have always struggled massively with imposter syndrome. I started in the University of Plymouth and quickly found a job at Atlas 24 as a cybersecurity engineer. And I quickly found out that pen testing even existed as a role, and I was pretty excited to get started with that, but I felt like I would never, ever be qualified to do that kind of role. Eventually, after a bit of training and self-development, I did find myself doing application security pen testing at Atlas 24. And then I found out that all of my colleagues were really, really good, and I had just started and I was terrible. And eventually the company let me actually test real-world customer applications, and I thought, yes, I finally proved to myself I can do this. And then I realised that everyone else around me was reporting these huge critical findings, and I was reporting user enumeration via password reset for the 60th time today. So I decided that if I wanted to really be a pen tester and prove to myself that I would be good at this job, I needed to find some critical vulnerabilities, something to really prove to myself more than anyone else that I had what it took. And looking back on my journey as a junior pen tester, I think I realised that lots of people feel this way, and it's not a unique experience to me. Maybe this journey to finding your first critical vulnerability is actually required, and that by doing so, you'll quickly be able to prove to yourself that you have what it takes and constantly find amazing findings, just like my colleagues and I. So, off the back of that, I thought I'd talk a little bit about my experience as a junior tester, take away from lessons learned from those tests that I did back in those days, and then hopefully off the back of that, form some strategies that you guys can take away into your own testing and find some critical vulnerabilities. So, a little bit about me. Plymouth University, graduated 2020, straight into Atlas 24, been ever since. Cybersecurity engineer initially, ended up doing application security pen testing, and I'm now senior, which is good fun, but I'm still slightly worried about it, and the imposter syndrome is still there, so hey-ho. Onwards, we're going to cover a couple of case studies today. These are real case studies on real customers that I can't name, from my first 2 years as a pen tester. Then we're going to summarise some lessons learned out of that, and hopefully we'll take away some strategies at the end. We'll summarise. So, let's get on with the first case study, a lesson in trying stupid stuff. The application itself looked a little something like this. This was a customer's instance of an API management tool. Basically, developers could log into this application, and from that they could read API documentation, they could read API keys that were stored in the application, and they could interact with these APIs via some kind of web console. So it looked like a pretty interesting target because it had lots of critical, sensitive data. However, as a junior tester, the only kind of apps I was allowed to test were things that had already passed through some much more experienced testers' hands. So they wouldn't miss anything, and I would be left with an application, and maybe I could report enumeration via password reset again, and I'd be moving on to the next app. But I didn't want that to happen in this case. In this case, there was actually an endpoint that seemed interesting. And that endpoint looked a little something like this. This is clearly meant to return your profile details as a user. And this was interesting to me because normally an application would simply check your session cookie or something like that and say, here are your details. But instead, the application was passing, in the big red box here, some kind of horribly complicated user ID. And I thought, hey, that's weird. Maybe if I take the user ID from a different user and put that in the URL, I'll get some kind of insecure direct object reference and read some data that I shouldn't have. That didn't work. 403 forbidden straight away, whatever. I was very upset about that. And just before I was about to move on from the test and complain to all my colleagues about how I could only ever find meeting risk vulnerabilities, I had one really silly idea. I thought, hey, maybe I'll run Brand Miner here, see what happens. For those of you who don't know, Brand Miner is a tool from Portsfigure that basically guesses up to 65,000 different parameter names in a single request, and if any of those parameters cause the application to respond differently, it will give you a little issue that you can go and investigate. And that's exactly what happened. A new hope. A secret input in the URL called UID, which immediately sounded kind of spicy. So, Brand Miner was basically adding a second UID to the query component of the request, and then adding some garbage data. And the application responded with some interesting things. First of all, the 404 error, when normally it would just be your profile details, and an error that specified user not found. So the question is, does this new UID override our existing UID in the URL? Because we're actually still providing my valid user details in this request. So I took another user ID and put it in that UID and kept the rest of the request exactly the same. And I quickly got back the response containing a different user's details. So this is my first clue that I have some kind of access control bypass on my hands. This special UID parameter that was hidden, that the parameter found, is overriding the UID in the URL. However, if any of you have done any kind of testing before, you'll know that this kind of user ID is not exactly predictable. I, as an attacker, can't guess that and then harvest all the information for all the other users on the application because it's way too complicated. The user ID of that length is going to take hundreds of thousands, if not billions of requests, so at most I have a really high access complexity access control issue, which is maybe a low or medium risk, not a critical. However, I kind of wanted to solve that limitation. I thought maybe, just maybe, there's a user added to this application that doesn't have some kind of complex user ID. There's no reason for me to think this. It's a really stupid idea. But I thought maybe there's like a default admin or a default user who just has a UID of, I don't know, maybe 1. Oh, there is a user ID with 1. The administrative user has a UID of 1. So now I have a real access control issue with a predictable exploit. I can just add $UID equals 1, that is actually the entire exploit for the rest of the presentation, by the way, to any endpoint, and suddenly I'm an administrator in some sense. Now I thought, okay, all I'm getting so far is the admin's email. That's not very fun, but maybe I can use it somewhere else. The obvious choice for me at that time was update user, right? Maybe I can change the email and lock them out of the account. That didn't work. The accounts were linked to Office 365. And the email was basically a placeholder. It was more like a username more than anything. It did nothing else, just changed some text on their profile, which is bad, but not in any way good. I could also change their password, but only if I knew their existing password, which is an access control issue that you can almost never exploit. So I thought, anywhere else in the application? No, because those APIs that I could interact with all had other unpredictable IDs that I couldn't use. So I sat there for a bit, made myself very sad, and thought, well, maybe I can report a slightly better access control issue. Now I can edit some data and read some data. Maybe this is looking at a kind of median at 6.5 on CPSS or something like that. Not the end of the world, better than my usual finds at that point. But then, just before I report the vulnerability, I had another idea. Or rather, actually, I just remembered something. Didn't I get some API documentation with this? Yes, I did. The API documentation contained a generate single sign-on URL that was completely unlinked from the rest of the application. For those of you who don't know, a single sign-on URL is basically a one-time login token that you can paste into a browser and it allows you to log in as the user without knowing their password. That might sound a bit insecure, but it's usually so that on your laptop you can generate this link, send it to your phone, and then you can log in without having to type on a tiny keyboard or something like that. And obviously, it's only meant to generate a single sign-on URL for your own user. But I have the power of $UID equals 1. So I added UID equals 1 to generate a single sign-on URL and ended up with a single sign-on token for some kind of user, which I was hoping was the administrative user. When I pasted that into a browser, I ended up on this page, which doesn't look like much, but this admin user had access to every single user on the application with full read, write, delete, create, updatability, or CRUD operations, I should say. I had access to every single API stored in the application, including interacting with those APIs and their API keys. And finally, in the horribly drawn red box on the left, I had access to the application's content management system. So I could edit any page, I could delete any page, I could add my own pages, host malicious content. I basically, at this point, owned the entire application, which is pretty critical. So I reported that to the customer, and I was very happy with myself. Though actually, I still had a few more mistakes to make along this journey, which led to a series of very fortunate events. In December of 2022, I reported this, which is actually my first ever critical finding, to the customer, and I was really pleased with myself. I'd proven to myself I had what it took, even if it was ridiculously simple and required basically guesswork. I got there. In January of 2023, the customer reaches out to me and says, we can't fix this, we're going to contact a third-party vendor, which is pretty normal. Customers often blame third-party vendors for no reason, and I thought, that's pretty normal. Anyway, about a week later, I get an email from the third-party vendor that basically said, yeah, that's actually really is our fault, we're sorry, And that third-party vendor turned out to be Microsoft. Turned out to be the cloud engineering team at Azure. And they said, by the way, we run a bug bounty program if you're interested in reporting it there and maybe seeing if it works. At which point I realized the application I was testing was a customer's instance of Azure's API management software, which means I had a good shot at maybe my first bug bounty along the way. So, in the middle of January, I recreated the issue exactly as I did in the customer's environment in a default instance of Azure, and it worked exactly the same way, unbelievably. So I reported it to Microsoft, and in February, the following month, they reported it by obviously removing support for the UID parameter. If you bypass this, amazing. Let me know how you did it. I've tried, I failed. At the end of January, though, I received the best email I've ever received in my career to date, which was basically, by adding UID equals 1 to the end of the generate single sign-on URL, Microsoft are going to give you $10,000 US. Which I almost missed because I didn't notice that I was testing Azure and not the customer's application. But lesson learned. So, off the back of this, I have my first critical vulnerability, an amount of money that I did not deserve, and some lessons to learn. When I first presented this finding to the application security team at Albus 24, the only lesson I could really come up with as a junior tester was run Brown Miner. It's pretty good. Maybe you guess it now. But looking back on it now, I think there are several really important lessons we can take away from this. The first and foremost being, try that stupid idea. I cannot stress this enough. People skip the obvious stuff, especially in web testing. Maybe because it's all slightly obvious in web testing. I don't know. But try that stupid idea. You'd be surprised how often it actually works. Always refer back to your discovery phase. I know everyone always harps on about reading your API documentation, and I had read it before the test. I had known that endpoint existed, but I forgot about it, and I thought, API documentation, I'm not going to read that a second time. But because I did, I found the pathway to the critical exploit. So always refer back to the data you have, especially before you're going to report an access control bypass. You need your full attack surface. Don't skip steps. Always ask yourself questions and iterate. Throughout the slides, hopefully you can see my insane thought process of just guessing stupid things and then seeing if they work. If you ask yourself silly questions and then just iterate to the next step, you'll find that you don't miss things. Break it down to logical steps. If you find a user ID that you think might be an idle, see if it is. Okay? If it isn't, no problem. Maybe there's a user ID that's less complicated. Maybe UID 1 equals works. In that case, it does. Always iterate on a question until you're completely out of ideas, including the stupid ones. And finally, always push for maximum impact. Show the customer how much this damage, this vulnerability can do in their environment by pushing as hard as you can to push a finding from a small access control issue to a $10,000 bug bounty somehow. Right, that's it for case study number 1. Case study number 2. Excuse me. Let's try embracing some complexity. It's not going to hurt too much, but we'll see. A little bit of a disclaimer. This is a particularly complex topic called request smuggling. If you've never heard of it, you may not understand what's going on for the next 20 minutes. But don't worry, that's kind of the point. I just want to highlight to everyone that if you have no idea what's going on for the next few minutes, we're still going to come back and learn some lessons, and all I want you to take away is not to underestimate complex topics. Now, at the time of this vulnerability, that's exactly what we were doing at Albus 34. Some new research had basically come out about HTTP2 request smuggling, and we were all really excited about that, and looking at that and going, yeah, let's go find loads of vulnerabilities about that. And we'd all sort of thought HTTP 1.1 request smuggling is old now, it's not cool, vendors will have fixed it, there's nothing to find, whatever. But since I wanted to find things that no one else was finding, and I wanted to find critical vulnerabilities to add some confidence to myself, I kept looking for request smuggling in HTTP 1 on every single app I had as hard as I could, and it failed for months. But then I came across this application, which was a login page, because the customer didn't provide accounts before the pen test started, which never happens, of course. So after testing the username and password fields and finding that the application wasn't vulnerable to anything, I quickly found a version parameter which reflected some content, but wasn't vulnerable to cross-site scripting or template injection or anything fun. So I was going to email the customer and say, can I have some accounts, please? I can't test your application. But a tool called HTTP Request Smuggler suddenly came back with a ping saying, hey, maybe request smuggling. And this is another tool from PaulSuite, by the way. This, as exciting as it sounds, actually filled me with dread. Because I knew quite a lot about HTTP2 request smuggling, but nothing about HTTP1, and I thought it was going to be really complicated, and I have no idea what I'm doing, I need to ask someone for help. I have no idea, I've only got a few days on this test, I surely can't handle this right now, who am I going to speak to? And then I thought, you know what, screw it. HTTP request smuggling can be supercritical, I'm just going to learn it as I go. What's the worst that can happen? How can we confirm that we have request smuggling? Well, this is where it gets a bit technical. So, in this particular case of request smuggling, the front end and back end server existed, first of all, just the kind of architecture of the application. And if I send a request that looks a little bit like this on the left-hand side of the front end server, you can see it's a HTTP 1.0 request. It contains a transfer encoding chunked and a content length header. These two headers basically represent the message lengths of requests heading to the servers. Two different ways. The transfer encoding should always be prioritized. So the front-end server prioritizes the transfer encoding header, and everything in yellow gets sent to the back-end server. So far, so good. The back-end server, however, is a bit more strict with its request parsing. It says, this request is 1.0. In 1.0, the transfer encoding chunked method didn't exist. I'm going to ignore it. Fair enough, that's RFC compliant. When you do that, however, I've maliciously set the content length to 4, which ends just after the 4.3. The red 4.3 and then 2 new lines, meaning 4 bytes, which leaves behind in the response, or the request queue, something that looks suspiciously like a new HTTP request, or a request prefix, as we're going to refer to it. And now we end up in this situation, where the back-end server is still reading the content length. It's responded to the previous request, because it's read in the data that it thought was there, and it's left some data on the socket, from a technical perspective. And the content length is set to 15, which is larger than x equals y and the new 0. Basically, the backend server is saying, hey, where the rest is my data? Where is the rest of my data? So, when a new request comes along, say a request from MoProfile from some victim user, rather than responding to that on its own, that actually gets appended to our request prefix's body and interpreted as the same request by the backend server. So the backend server then responds with a 404, and the person who sent this initial MyProfile request is confused. If you're all still confused, don't worry, it gets much worse. The next slide is a view from Burp Repeater. I'm going to send the exact exploit I was just sending, and you can see initially the application responds with a 302 found, and then randomly it starts going 404 not found. Which all it proves is that in my application, you can see I was excited because I'm waving my mouse around. All that really proves is the application is actually responding to our prefixes. They're kind of in front of the request in the queue, and that means that we can manipulate other people's requests. However, because request smuggling is annoying, this behavior does not confirm request smuggling entirely. And you can see that in documentation that I learned from, which is all Swigger. The attack request and the normal request should be sent to the server using different network connections. In this case, the normal request, by the way, is just the request that comes next in the queue. The attack request is the one that sends all the complex data messages and stuff like that. So, there's a good reason for this, and that's because front-end and back-ends have lots of different architectures. The most common, or we usually see, well, actually not the most common, but one of the options you can have, is that every connection to the front end has its own connection to the back end, which means that your request prefixes can only affect your own connection. Not very useful, it's called a self-desync. DefParam has an amazing talk on this, by the way. You should go check it out. There's a little link there, which you can't see, but I'll share the slides or something. The second one is an IP-based desync, where, for performance reasons, anyone on the same public IP shares the same connection between the front end and the back end. Now my request prefixes end up on these queues, meaning that they can actually affect other users on the same network or on the same VPN, for example. And finally, we have a completely open desync, where the front end and back end prefer performance so much that rather than creating any new connections, they just have one massive keep-alive connection where all data from all over the internet that tries to access the application goes through the same pipe between the front end and back end. This is called a keep-alive connection, and this is the scenario we have. This is the most critical because it means my request prefixes can hit anyone on the internet. So, with that in mind, let's move on to actually building an exploit with request smuggling. There's a big list from Portswigger that you can try here, and I tried bypassing front-end security controls, but the application didn't have any because of the login page. I also tried exploiting cross-site scripting findings and making them more impactful using request smuggling, but I couldn't do that because my reflected content wasn't on cross-site scripting. And I also tried making an open redirect happen, which is about the most dull you can make a finding in AppSec. Open redirects are everywhere. I didn't want to report it as an open redirect. So I ended up focusing in on capturing other users' requests, which sounded pretty damn critical. However, After I dove into the documentation, I quickly reached a blocker, which is that to capture other users' requests, you need a place to store them. You need like a comment section on the application so that when you refresh the page, you get that data back. Now, I did have that version parameter on the login page that reflected content, but that really wasn't persistent storage. As soon as you refresh the page, it goes away. So, just before I was about to report this as an on-site redirect to an open redirect using request smuggling, which is cool proof of concept if you're technical, but dull in terms of impact for the customer, I decided, screw it, I'm going to do some research and make this schedule. I was not having it. I was sad about this not working. I missed that part, sorry. So, after 4 days of research, this is a true story, 4 days of research, I finally came across a talk from Martin Duykenard, who now works at Volkswagen, on response smuggling. And in his research, he had found that he could make request hijacking possible without persistent storage and with just reflected content. And I thought, hey, I've got reflected content. Maybe I can do this. But it also required something called desynchronization, which it turned out was actually another word for response queue desynchronization. Now, that sounds very confusing, and it is. We'll cover it in a second. I actually knew a little bit about this because it had been released in the HP2 request smuggling research. And I thought, hey, that's pretty cool, but I had assumed it only worked in HTTP2 and not HTTP1. However, if you read the Volkswagen documentation very carefully, it actually tells you that it's possible in both versions, so I could have saved myself 4 days by just reading that page slightly better. But hey-ho, let's see if we can make response queue poisoning happen so that we can capture requests. We have a reflection gadget, now let's prove response queue poisoning. So, this is where my animations come into play. I apologise, they're all terrible. I'm a pen tester, not an animator, but it does explain it better than HTTP. So, it's so pretty. The attacker sends a request to the front-end server, and the front-end server sends this time, instead of a request prefix, we're going to send one whole request. And the reason for this is that we're hoping the back-end will basically generate 2 responses to our smuggled request, generating an extra response, which causes something like this. The back-end server sees 2 distinct requests. These are whole requests, and we'll see a bit more about that later, so it generates 2 responses from a single request. Okay? When these responses make it to the front-end server, they're now in a queue. So, well, the front-end server just knows that one person sent a request, so I'm going to respond to that one request with the next response in the queue. So the attacker receives their response. But now I have this yellow blob left over. What happens to that? It's okay, don't guess. Let's look at a proof of concept of exploitation, because it makes it a bit easier. First, the attacker sends the exploit to the front-end server. The front-end server receives 2 responses from the back-end server. So, since the attacker just sent a request, the attacker receives the attacker's response, leaving the attacker's smuggled response, the extra response generated, in the front-end queue. Hopefully, the victim comes across next and sends a request to the front-end server. Their response is generated by the back-end and added to the queue from the front-end server. So now when the victim's request is being handled by the front-end server, they receive the wrong response, the attacker's smuggled response, the extra response. Right? Pretty bad. And of course, as an attacker, if I time it right and send one more request, I now receive the victim's response. This is terrible news for HTTP applications because it basically means that you've caused a chain of destruction where everyone starts receiving the wrong responses in the application. And you'll leak sensitive data all over the place to anyone on the internet trying to reach the application. However, there is a big limitation. First of all, you need a very high volume of traffic to make this work. You need all the connections to be consumed and for things to kind of go mad. And I was in a pre-production environment. By the way, don't ever do this on a production environment. Customers will get very angry when you start desynchronizing clients' data around. Because it's so inconsistent, you also don't know what kind of sensitive data you're going to get back. If you want to capture a session token, you need the victim to be logging in as you trigger response queue poisoning and hope that you're the one to get their login request, and then you'll just end up magically logged in as the user, which is cool, but really unreliable, unless you want to really hijack the site. So, I was going to combine this with our reflection gadget, as Martin said in his talk, to make this more consistent. So now we have a reflection gadget, and we've proven that response queue poisoning actually works on the application. And it did. You just send one full request rather than a request prefix, and that behavior just sort of happens. Now that we have this, we can look at the final exploit. I'm sure this all makes total sense to you, right? No, it's okay. I'm going to break this down again with some horribly drawn boxes. The final exploit request uses two smuggled requests. The first is the response queue poisoning request, which is going to trigger the same behavior we just saw. And the second is our reflection gadget on the login page, and that is a request prefix. That's why the orange box goes to the end of the request. It's going to wait for more data. So, the blue box looks something like this. It's a HTTP 1.0 request with the content length of 4 and a transfer encoding set relatively. This will cause backend and frontend to disagree about this request being one request or 3. The response queue poisoning request is a JavaScript file, and it's one whole request. And you can see that because the content length is set to 3, and the body is set to x equals y, which is 3 bytes of data, right? This will instantly generate a response on the backend for a big JavaScript file, and cause the response queue desynchronization. Finally, we have the reflection gadget, which is a post to the login page, and it has a massive content length of 10,000, which will hopefully be enough to make the backend wait for enough data from the victim's request that it gets appended to our version parameter, reflected in the login page, and then, because of the response queue desynchronization, we'll have captured the victim's request. Yay! Makes sense? No? Well, don't worry. The flow of this is even more complicated and has even more pretty boxes. Okay, so, again, I'm not an animator, I apologize for this. The attacker is going to send their exploit first. This reaches the front-end server as normal, and then goes to the back-end server. Right after this happens, the victim sends their request. Then, the backend misinterprets the request lengths and splits it into 3 distinct requests. Because the reflection gadget is a request prefix and is waiting for more data to arrive, the victim's request actually gets appended to it. See that? It's all one box now. And just after that, the attacker has to send their follow-up request. That gets added to the backend, and then the backend can start responding to these requests. The attacker sent their request first, so the attacker response gets routed to the attacker. The victim's request was hopefully next, so they get the random JavaScript file that we smuggled to the backend. They're like, what the hell? And the attacker, who hopefully came in just at the right time, finally receives what was meant to be the victim's response, that is actually the reflection gadget containing the victim's request, resulting in request hijacking. This is as simple as I can make it. If it's still confusing, don't worry, you'll see how it looks on the next slide. Again, this is pretty unreliable. It's very timing based. The attacker requests have to have a victim request right in between, and the timing is very sensitive. So, to make it a bit more reliable, we're going to ramp it straight up to light speed using a tool called Turbo Intruder. Again, from Vulns. This is a very simple tool. It takes a HTTP request of any format and spams it at the application as fast as it possibly can. That's it. It's a big grey box. Every new line in this grey box is the HTTP request exploit being sent to the application. And that's what we're going to see. I'm going to talk over this, but if you just like watching Turbo Intruder do this thing, just watch and try to read the tiny text. I'm going to hit attack. And then you're going to start seeing Turbo Intruder spam the application with our exploit. In a second, I'm going to halt this request and then look for 200 responses, which are going to basically contain captured requests, hopefully. The first one I'm going to check here, a little bit ahead of myself, is actually going to contain our own request. Because the timing wasn't right, we just captured our own request, and you can see that here. I search for exploit, and the request body contains our exploit request. Failed. But the next request I check does definitely contain a victim request, and I can tell this because it contains their access token, which is what I use to authenticate as the victim. So at this point, the victim has just interacted with the application, like as in visited the site or clicked a link, and now I have stolen their session, and I can completely take over their account. Pretty critical. Now, one of the benefits of this kind of exploitation is that it is internet-wide, right? I know it's an open desync, so it will affect anyone trying to access the application at this time that I was running the exploit, including my colleagues. I quickly noticed I was capturing access tokens for people that weren't me, including my colleague, Volvet, who said, yes, that is my access token. He didn't know I was doing this, by the way. I just sent him his access token and said, is this yours? I said, yes. The point I'm trying to highlight here is that this affects anyone accessing the application simultaneously. So if I just run this exploit for a day, I will eventually capture the session token for every single user accessing the application from wherever they are on the internet. Okay, resulting in an application-wide account takeover vulnerability that requires, well, user interaction in the sense that they're using the application, but basically no user interaction. Possibly the most critical finding I have to date, by the way. So yeah, A pretty powerful exploit, very complicated. Some lessons off the back of this. Run request mode, maybe. It's pretty good. Find your big stuff. It's only going to tell you that you have between a desynchronization between the front and back end server. So it will give you some clues, and then you can figure out the rest on your own, which, as you can see, is a little bit complicated. It changes from time to time, but once you get the hang of it, it's still pretty complicated. Question your assumptions and read the documentation carefully. For a second time, I almost missed out on a huge vulnerability. 4 days of research could have been taken down to 5 minutes if I'd just realised that response-to poisoning was possible on HP2 connections and HP1 connections. When you read documentation, if you're really lazy like me, Control F, search for security or notes, and they'll be the bits that you didn't read, and they tell you how to break applications. Search, learn, and improve. Don't rely on one source. Most of my exploits come from Portsfigure and things like that. And when they do, there's still things that we miss from there, so obviously use multiple sources, but also, even when you think you know loads of things about a topic, still go away and do some research on the day. You'll be surprised what you found. It took me 4 days, but eventually I found an exploit that made this finding absolutely bonkers in terms of criticality. Always push for maximum impact. It's actually okay to spend 4 days doing research. I didn't get told off for doing that. I didn't even get told off for not reading documentation in the first place, okay? If you're spending half your time pen testing using Google, you're doing it right. Good job, okay? It's not a problem to be Googling all the time. Embrace it. Always push for maximum impact. And finally, embrace complexity. It really isn't going anywhere. I now have a much better understanding of HTTP request modeling, and it still scares me. And even though I have a good handle on that kind of vulnerability, I still don't know how to do a race condition. I know what the new tech looks like, but I have no idea where to find them, or look for them, or exploit them. Complexity isn't going anywhere. Embrace it now, and for the rest of your career, you'll be wondering, why is this still really difficult? It just is. Pen testing is hard. Embrace it. That's it for case studies. Let's try and quickly go through some strategies. Right. So, first of all, strategy number 1. Let automation complement your testing. Don't be afraid of it. When I first started at Outpost, I was both told and myself felt that automation was very scary, not reliable, and that I shouldn't use it because I'll crash applications. And you definitely can. If you run Ferox Buster on an application, which is just looking at the URLs, you can crash really, really rubbish applications instantly. But don't be afraid of it. If you need to, rate limit it. If you learn it, understand it, use the reliable tools. If you have to build it yourself because you're so distrusting of other people, go ahead and do that. But do not ignore it. You will be left behind. Okay? We need automation these days, especially for the size of the applications that I have to test within 5 days these days. It's ridiculous. Embrace it. Abandon scanning for vulnerabilities. Unfortunately, we're way past the point of no return on vulnerability scanners being 100% accurate. They're fine these days, okay? We've got some really good ones, but they're not going to spit out criticals every time. They might occasionally spit out a cross-site scripting vulnerability or a SQL injection vulnerability, both of which are great. 1% of the time you're going to get one of those and you can feel good about scanning. But if you abandon the idea of it actually spitting out vulnerabilities and instead allow it to find clues and breadcrumbs that you as a human can put together and build a vulnerability, you're going to have a much better success rate. Seriously, use vulnerability scanners. They are the best fuzzers on the market, and they can apply logic, and you can just learn from their results and focus your testing on the weak areas that vulnerability scanning can tell you about, but not exploit by itself. Embrace the fuzzing potential. Pretty similar. I see lots of people open stuff on their terminal and then start fuzzing applications one parameter at a time, and it takes them months to test an application. Use a vulnerability scanner on just that parameter. It will test more payloads than you could ever have imagined, and it has logic behind it that says, if this payload doesn't work, it's not vulnerable to that, I'm going to move on. Once you have some clues, then you can involve manual fuzzing. And finally, make testing stupid ideas quick and easy. By running tools like Param Miner and HTTP Request Modeler, you can look for things that no one else is looking for. No one else is thinking, I wonder if there's a hidden parameter here that bypasses access controls. Why would you? That's completely nonsensical. Why would the developers leave that in? I don't know. Ask Microsoft. But if you make it easy by automating those tests, you can just run them and then forget about them. And if you get a hit, congratulations, you're going to get a huge fine. Maybe. There's no guarantees. Strategy number 2, try that stupid idea. Nothing is too obvious. Something I tell our new unit testers is, if you find yourself thinking that's too obvious, everyone's tried that, try it anyway. Because everyone skips the obvious stuff, and you'd be surprised how many findings I've gotten by just trying stupid stuff and not thinking that's too obvious. Literally catch yourself thinking that's too obvious and go, no, I'm going to check anyway, and you'll be surprised how often that actually works. Embrace simple thinking. All I mean here is don't overcomplicate things. Break it down into the most logical steps you can. If you're learning request smuggling, take it one step at a time. And if you're learning to break an ID because it's too complicated, again, take it one step at a time. Does a different user's ID work? Yes, no. Does user ID 1 work? Yes, no. At least you've checked, right? Break it down. And introduce stupid ideas into methodology. If you don't check with this stuff, you're never going to find it. So use automation, put it at the beginning of your methodology, check for it really early on, and then forget about it. And the one time it works, you're going to be happy. Strategy number 3, step back and reflect. Question your assumptions, even if it means stating them out loud, and I do this quite a lot. Question your assumptions. Again, this comes back to my mistake on HP2 versus HP1 and response queue poisoning, but just question your assumptions. Read the documentation a second time. Obviously, perhaps, but this time I want you to read it as an exploit development guide. Read it before you start testing the app so you know what the app does, and then halfway through your test when you've got a bunch of things that maybe you can work with, reread the documentation and it will teach you how to break it. That's what documentation is for. If all else fails, talk to the rubber duck. If that doesn't make any sense, you should look up rubber duck debugging. Basically, talk to an inanimate object or a person who doesn't understand your issue. They have to say nothing. They can just be having a cup of tea. It can be a parent, a friend, a grandma, doesn't matter. And just explain the issue as logically as you can out loud. And you'll quickly realise that you're an idiot and that you've made some mistake with logic or assumptions, and you'll be able to debug the issue. You're probably going to see this a few times, but check out the website, it's awesome, and they have links for ducks you can buy, etc. Strategy number 4, embrace complexity. Imposter syndrome is never going away. It hasn't gone away for me. I don't know anyone who has ever managed to beat it in my team. Everyone still feels this way. Just embrace it and you'll feel much better about yourself. If you're feeling totally out of your depth, you're probably just about in the right place to learn that new technique that you're terrified of. It worked for me with request smuggling and it's worked since then as well. Just embrace that rock in your stomach that makes you feel not good enough and have fun with it. Test the hard-to-test features. Complexity can come from the application just being very mean. If it delays all your requests or there's a web application firewall or there's loads of dynamic value you have to update, set up a scanner that can use those things with some kind of session rule and test the features that everyone else is too lazy to test. We're all pen testers, and I think we're all really lazy. So just test the hard-to-test features, and you'll be surprised at the critical vulnerabilities that will be hiding behind those things that are just a bit too difficult to scale. And finally, always push for maximum impact. Critical vulnerabilities are not found, they are forged. Think about what is possible in the application, how to exploit it will come naturally later. Off the back of that, if you chain more things and then think about what else you could chain, all those medium recommendations that you make to customers often can be chained together into critical vulnerabilities. If you report cross-site scripting and a cookie missing HTTP only, or a cookie or a session token stored in local storage, again, one more time, without also reporting that the cross-site scripting can be used to steal that token, I will lose my mind. So always chain your vulnerabilities together. A reflection on the login page that is not vulnerable to anything is useless. It's not even worth reporting to the customer 99% of the time. But if you have request smuggling, it suddenly enables you to capture users' requests. So it's worth keeping in mind all the small things you found. And finally, read, research, listen, and then repeat. I know you're all staying up to date. That's why you're here today. That's really good. But when you come across your next cross-site request forgery finding and you think, that's outdated, I know what I'm doing, go away and do a little bit more research on it now, because you'd be surprised at what people are finding now that bypass the same site restrictions as well as same origin. It's kind of crazy. So stay up to date and then stay up to date a second time when you find a vulnerability that you think you understand. To quickly recap, let automation complement your testing. Try that stupid idea. Step back and reflect. Embrace complexity and always push for maximum impact. Thank you very much. Don't forget to follow me on X. That was my boss.
Thank you, brilliant talk. We've got 1 minute if we've got any questions, so perfect timing.
Yeah. Any 1 minute questions? Yes.
Did you get to keep the bug bounty from Microsoft, or did that go down?
No, they have a policy. You can keep it as long as you write a blog post about it, which is on the website now. Along with my colleague's blog post on basically the same vulnerability, but in HTTP2 that we found literally a week after I found mine, based on the same research. So yes, we did. I spent it on piano. The first part of it, at least. The rest of it is saved. Anything else? All right. Thanks very much, guys. I really appreciate it.
Thank you.